mentioned yesterday, one of the 4 projects that have been allocated to the University of Bristol for ERIES projects, and one of the 2 that have been completed. The other has been partially completed. This has been fully completed on the experimental side. So I'm going to report the main findings from the preparation, from design of this test and execution of the project. Special thanks are due to Professor Maria Pina Limongelli, that led the effort on behalf of the user group, and to Dr. Dimitris Karamitros, who led the management of the project and the meetings and the design on behalf of the University of Bristol. Only few people are listed here, people that have either they were either leading or co-leading the project, and those that have visited Bristol and taken part in the experiments. Dimitris, who is shown there, second from right, put significant effort, so special thanks are due to him. He has also put together the slides. All the credit goes to him for the nice slides, and any errors that I'm going to make in interpreting them could be, the blame could be put on me. And you can see also the 3 visitors that came to Bristol to execute the project last June. Now, why did we choose this project and choose to start with this project? There are 2 reasons for this. The first reason is that we thought it was simple. At least we had this impression initially, but it was the wrong impression. It took us, you can judge how difficult is it to place a single oscillator resting on a footing on a, ordinary, relatively large, but nevertheless ordinary soil container, laminar container, and shake it, following a little bit of scouring artificially the base around the footing. It looks very simple, and you might think that it might take less than a month or 2 to carry the research out, but that was not the case. It took us more than 2 years to deliver. And the second reason was that we had not used a lot the shaking table, the new shaking table at the SOFC lab, so this is basically the second test and the first important, let's say, ERIES level test that we carried out. And hopefully I'm going to convince you that we had to navigate in a dark room in order to design the experiment, not putting blindly a specimen and shake it. The team, as I mentioned earlier, is much wider, comprising approximately 25 visitors from across Europe, and the University of Bristol team was quite wide and strong as well. I would like to acknowledge the contributions of Raffaele De Risi and Flavia De Luca that are in the room today, as well as Tansu Gotche, our postdoc, who did magnificent work in carrying out the tests. And starting with the concept, I don't need to convince anyone as to the importance of scour in bridge engineering. We know that bridges fail due to scour much more often than due to earthquakes. Maybe the ratio of scour-induced failures over earthquake-induced failures could be 5 to 1, 6 to 1, 7 to 1. It is very, very a significant mode of failure. And what we tried to do here was to try to understand what would be the additional aggravating factors and the additional damaging factors and the additional risks associated with earthquake shaking in presence of some scour around a bridge pier. And this will be from the viewpoint of soil structure interaction, not with respect to wave scattering, but with respect to the modification in the natural period and vibrational characteristics in general of the superstructure due to the compliance of the ground. And this is an overview. It was carried out, overview of the experiment carried out in the large laminar box at the University of Bristol, which is almost 5 meters long, weighs, when filled, about 10 tons. It can be driven now with a new table, much easier than with the old one. In the old one was barely able to drive it, but now the 50-ton new one can very, very easily carry out these experiments with a filled box. This is a detail of the simple oscillator with resting on a caisson and a partially scoured base, as you see here. And I hope I'll be able to convince you that this type of design is not elementary. Just to give you a first taste, it also involves static bearing capacity considerations, the need to ensure that it's not going to overturn during earthquake shaking, and of course during gravitational loading before testing or after testing, because of the special nature of this foundation resting simply supported by soil material. The rationale, we were planning originally to test, in order to get more data, two structures simultaneously and compare their performance, but because of the interaction between the of the soil material between the foundations, that it was visible in the numerical simulations, we decided to limit our tests to a single structure at a time. The prototype, that was the first headache, and very, very important in my humble view. We were given by the user group this type of prototype. For the E-glide here, you can see that the natural period, for those of you that remember, is very, very close to the natural period of Hanshin Expressway in Kobe, the one that collapsed spectacularly and overturned in 1995, although the absolute level of mass and stiffness are approximately half of that structure. And one might think, well, job done. You can go to those nice tables, scale with the scaling factors, and scale it down to fit the box, and no problem. But the reality is usually very far from this ideal, ideal scenario. Why? Because it's an SSI problem, and part of the domain is sensitive to gravity, the soil around the foundation, but part of the domain is not sensitive to gravity, like the steel or aluminum parts of the structure. So using the tables, those that were put together over the years, first by the Japanese Kokusho NEI in the 1970s and 80s, and then by others, could be viewed as a recipe for disaster. The second problem with scaling directly down is that neither the earthquake environment is known a priori, nor the geotechnical environment, because, for instance, the sand all of us use in labs doesn't represent directly the real-life conditions where the material that scours could be associated with silts or clays, and of course involving water flow and the like. So there are issues that need to be addressed. That was the final design. One of the big headaches is to ensure that the connections were really rigid, so these fixities were respected by, assumed in analysis, were respected by the specimen, which was not elementary to achieve. We had to iterate here. And for reasons that I hope I'll be able to explain, we ended up testing two specimens, the so-called slender or flexible, which is about 32 centimeters tall, and a stiffer one, maybe a better word would be squat one. here which was only 27 centimeters tall, and you will see the difference, which is quite spectacular in the response. So two specimens tested separately for the reasons that I explained. Now the box can be shaken only longitudinally, does not respond transversely by design, and the orientation of that semi-ellipsoid that represents the scoured soil should be, of course, along the direction of water flow, hypothetical, of course, because no water flows in the actual physical specimen. And then, according to this motion we put, the bridge is excited transversely in the prototype scenario, which of course also indicates here that we are ignoring boundary condition effects at the abutments that induce additional constraints as to rotational response. But hopefully the main aspects are retained, and this is the geometry of the ellipsoid. It is important to keep in mind that this angle is approximately 25 degrees in the experiment, which is much less than the 32 or so degrees of the friction angle, the angle of repose of the sand, which ensures that no slope failures there will occur during shaking. And these are remedial measures that we're going to discuss at the end, related to grout, rock fill and grout put there to mitigate the effect of scour. Ground motion selection, this was handled by the user group. Basically, the idea is to come up with approximately spectrum-compatible motions that respect here the decreasing branch of the Eurocode spectrum. In the period range, these are fixed base periods of the stiff model, again at model scale, 3%, 0.03 seconds and 0.05 seconds, separating the stiff from the slender specimen. And this is for low seismicity, and we have a corresponding result for high seismicity. Keep in mind, of course, that we are going to have changes now in natural period, not only due to SSI, which is what we all do, but also due to scour. So there are two shifts. This period will shift to larger values, to higher values, first due to SSI and second due to scour, which is an additional effect. And how did we decide to proceed? By working analytically with simple model, 4 degree of freedom model, 2 translations, 2 rotations. This could be handled very easily by MATLAB or Python to allow us iterate quickly without having to do much with, put much effort with finite element analysis just to verify results. And this is perhaps the most important slide of the whole presentation. Again, this now is excitation frequency, not eigenfrequency, and you can see how the slender specimen responds at relatively low frequencies and how the stiff one responds at relatively high frequencies. And in presence of scour, those peaks will shift to the left as the material will be removed from the foundation. Now, if the soil in the container responds in the way you see here in the yellow curve, and for instance, you examine the red curve, you will see that the peak of the red curve is at the flat area of the yellow one. So there will be no appreciable effect in terms of SSI, nor in terms of scour. So as you move here to the left along this range, the specimen won't experience any difference in response. And that was the idea of using the two ones to bound the soil response to the left and to the right using a soft and a stiff specimen, but we had to make sure that the soil response was there in between, and they were sufficiently close. How easy is it? It's not easy at all. Why? Because all these boxes that are approximately 1 meter tall, I'm not talking about the boxes in Japan, in eDefense and other labs, have a very limited range of natural frequencies that one could achieve. And this is on the order of 20 to 30 hertz, depending on the sand. But in order to make sure that we could achieve lower frequencies, and that was the question here, we came up with some kind of an innovation, although it is straightforward from the structural dynamics viewpoint, to add some kind of isolation mechanism. So we added a rubber layer at the base and increased significantly the natural period, lowered the natural frequency in order to make sure that the yellow curve moves at the right place. I'm not going to spend much more time. The chairman is smiling at me. We have now carefully analyzed the response. You can see that the soil response is here, so the slender model resonates to the left of the soil peak. And if you go to the other one, the stiff one, you see that the soil response is here, but it resonates to the right. So it was after a lot of iterations, months of programming and optimizing the design, we came up with this solution. Now you can see for the stiff that the shifting period due to SSI is 30%, which is significant, very significant, if you look at the available data, which is not surprising given the stiffness of the structural model. And there is another 20% of so extra shift due to the scour. And we also tested some ground motions analytically to make sure that we have an idea as to the response that develops on the deck in order to make sure that it's not going to overturn during shaking, that the safety factor we want is not going to be well below 1. It was temporarily reaching 1, but instantaneously. So in the realm, for instance, the numeric sliding block that did not cause much problem. Summarizing, going very fast, all these findings were confirmed by the user group using a variety of software like COMSOL, Abacus, SAP, and others. And we instrumented it, both models, about 30 channels, including an Inmentrum camera you see there, because the displacements were small. And you can see here the targets that the camera was pointing to. And the pluviation took place with the help of a perforated plywood to make sure that the particles had the right energy to reach a relative density on the order of 80%. And we ran it. We can declare victory and finish. Yep, you can see how we produced the scoured zone with the help of the cardboard to achieve the desired geometry. It required some thinking, but I think this is a nearly optimal approach. And these are the remedial measures I showed earlier with a gravel and epoxy mixture. We have tested all these, and we completed the test in June 2024. So we can indeed declare victory and thank the people that worked in the lab to carry out the experiment. And we also recently deposited the data in the repository following according, hopefully, to the directions we had. It has not been released yet, but it is there. And with this, I would like to thank you for your attention, and thanks again also for your tolerance, Mr.
Thank you very much, George. That's a great presentation as usual. We are a little bit behind schedule, but I will allow for one question from the audience. If no question, I will ask you, did you see much of an evolution of the scour geometry during the shaking during the actual experimental tests? And were you measuring it?
That's a very good question, and that was a major concern. We discussed various solutions trying to avoid slope instabilities in that zone, and partially according to British standards and other regulations that led the user group actually proposing this type of solution. I mentioned that the largest slope here inclination, as you can see, was approximately 25 degrees. You can see the figure there, whereas the friction angle of the sand was about 32. So even if you include the effect of the horizontal acceleration, it was not enough to induce sliding. So to the best of my understanding, and I hope that this is that my colleagues Tassos, Rafael, Flavia agree that are in the room, we did not observe evolution of the semi-ellipsoid. That was a concern. Alternative ideas was to put some spray, some fluid, water, to induce negative excess pore water pressure after compacting a little bit, like you would do with sandcastles in the beach, in order to artificially strengthen the slope. But this wasn't necessary.
Thank you very much, George.
Thank you.
So now I was already expecting a little bit longer presentation by George, so he had a special allowance, but I will ask the other presenters to try to keep to the 15 minutes. So I call the second presenter, Francesco Ricciardelli, on the wind side of the project.
Well, thank you, Antonio, and good morning, ladies and gentlemen. What I'm presenting to you this morning is not rather results from one specific ERIES-funded project, but I would rather share with you some thoughts about the advantage that codification, in particular in wind engineering, can take from transnational research projects. But before doing that, I would like to express my gratitude to ERIES, because I was so lucky to be involved in 3 ERIES-funded projects. First one is about the rain-wind cable surface modification of stay cables for reducing rain-induced vibration. And the project is led by Christos Georgakis from Aarhus University. And tests were carried out at CSTB in November last year. And thank you very much to Olivier Flamand that assisted that. And the second one is ERIES switch rough on the effects of changing roughness of the ground on the flow characteristics in the ABL and on the loads on vertical structures. And this project is led by Fabio Rizzo from Politecnico di Bari, and tests were carried out less than a month ago in TU Eindhoven. Thank you very much to Stephanie Gilmeyer. And third one, actually tests have not yet been carried out. That the principal investigator, it's me here. Tests will be hopefully carried out in August this year at Western University. And thank you very much to Girma Bisumlak and the whole staff there that is helping very much in organizing tests and assisting with the preliminary things. But let's go to the main focus of this presentation. Now, most of you are aware that the transition towards the second generation of the Eurocode started back in 2012 with mandate 515 of the European Commission to SEN. And as far as wind engineering is concerned, the activities started in phase 2 in 2017. And the project team of 5 members that had the chance of being a member of prepared the draft. And now the draft is going to the formal vote to take place in October, and I'm the convener of the task group that is doing this work to take the document to the vote in October. Now, there have been long 8 years of work on that, and we all, a large number of people working on that at the different stages, we all realize that there are several shortcomings which are associated with the calibration of the code on wind actions. And These shortcomings mainly come from the fact that data that we avail for it were produced independently from several labs and research institutions in the 70s, 60s and 70s and 80s of the last centuries. And due to that, the data are sometimes heterogeneous, sometimes they're inconsistent with each other. And we also know that we have much better measurement and processing techniques nowadays with respect to the ones that were used at the time. And most of the data sets are incomplete. There are several design situations that we would like to account for, which are not incorporated in the present code. And finally, perhaps the most important thing, the data that we have do not reflect the reliability approach which is given in EN 1990. So they're not consistent with the structural reliability approach that we have to use for the Eurocodes. Now, when I say code parameters, I can divide them into site-dependent code parameters and site-independent code parameters. Now, for site-dependent parameters, there can be done two different things. One is to calibrate them at the national level. So at the European level, the only thing we can do is give rules to do that, so to make the data and the results consistent with each other. The other option is to calibrate them at the European level through joint research and through some consensus to be reached among the different national standardization bodies. Then there are site-independent parameters, which we can draw them from the literature, and of course there must be some consensus on the data at the national and international level, but also we can produce new data at the European level. And I believe that these two red lines here are the ones where transnational research can help very much, can assist very much in producing new data and looking at old data as well. Now, if we interpret the load equation given in the Eurocode and in several other codes through the Allen Garnett Davenport wind loading chain, we see that the first four links of the chain corresponds to the four terms that appear in the load equation, the equation that is giving rise to the characteristic value of the load, and the fifth link is the one associated with code parameters, that is partial factor on actions and the combination factors. Now, at least 3 out of those 5 links can very much benefit from results of new experiments, new experimental activity, and joint research at the European level or international level. Now, code parameters in wind engineering can be calibrated in at least 3 different ways, or at least using 3 different tools, which is wind tunnel testing and full-scale testing and computational methods. Now, I'm giving you our very personal and short list of places where new testing can help very much, in our opinion. For example, as far as the ABL flows are concerned, what is not fully explored is what is the effect of a roughness transition, and I will say a few words on that, the effects of orography, the characteristics of flows and actions in the canopy layer, and of course the effects, characteristics and effects of non-synoptic winds. And as far as aerodynamics is concerned, of course, we can derive different sets of aerodynamic coefficients for wind tunnel tests. If we go to full-scale testing on the other side, again, we can try to investigate the effects of orography in real setups, the effects of flow characteristics and effects in the canopy layer, and again, the effects of non-synoptic winds through full-scale measurements. But also, we can use full-scale experiments to validate existing model and their calibration. Finally, there are computational methods, and I will divide them into CFD methods, which we can use for evaluating, for example, again, the effects of orography or the flow in the canopy layer, but also what is very fashionable nowadays, which is climatic reanalysis, which we can use to supplement measurements to evaluate wind hazard. Now, there are at least these ones that I marked in red now, which are topics which has already been dealt with within ERIES funded projects. And here is a list of projects that have been run and that can somehow already, with their results or, results that will be produced, assist in this procedure. And I will a little bit just shortly concentrate on the last 2, which are the 2 ones that I'm involved with. And so I will say just a very few words on one or the second one. Now, just to give you a few details on that list, just one first item can be that of the characteristics of the ABL flow and of the wind loading after a roughness transition on the ground. Now, what we do now is to rely on the model presented by Dives and ERIES, which was incorporated back in 1984 in ESDO, in an ESDO item, based on numerical evaluations which were made in the 70s, that is with a very limited computational power available at the time. Now we have much better tools. But the thing is that then that model was incorporated into the Eurocode, into the ENV version, ENV 1991-24 in 1995, and then it was moved to the current version of the Eurocode in 2005. Now, the approach is based on tables like the ones that you see here, where the fetch length upstream a structure to be considered is given as a function of the height of the structure that is under design. And just to make you aware of what's going on here, if somebody wants to design a 50 meters tall structure after a transition from Eurocode roughness category 2 to Eurocode roughness category 3, he or she should be looking at a fetch of 30 kilometers upstream the structure, upstream the construction site. And that, of course, something that no one wants to do and nobody actually does. And in fact, that's the reason, the main reason why this procedure has not been moved to the new version of the code for the second generation. So something new is needed here. And in fact, this is the main focus of the project ERIES with RAF. Again, I said the tests were carried out less than a month ago. And what we did there, I'm not spoiling the results and the activities that were led by Fabio very nicely, but basically what we do is we took advantage of the very long fetch available in the TUE wind tunnel in Eindhoven, and we could reproduce equilibrium profiles from the Eurocode as well as transition profiles, and then we will be processing pressure data measured on a vertical structure to see the differences, investigate the differences, and hopefully come up with the simplified model to do that, which should supersede, hopefully, the model by this and Earth. As said, another project that I'm involved with is ERIES TWA, which is on the thunderstorm winds. And the idea behind the project is that until now, all research activities on thunderstorms and their action on structures were mainly devoted to the physics of the process, that is, trying to understand and describe the physics of the process. No mathematical description has been attempted yet. So the idea was to make a very large number of tests, hopefully we will be able to do that, and try to probabilistically model the results of this test in order to get a probabilistic model for the description of the actions. Now, as said, there are several other fields of activities where transnational research can help very much, and perhaps one of them is evaluation of wind hazard. The current wind hazard map of Europe is the patchwork of maps that were produced nationally in the last 30 years, using heterogeneous data, different procedures, not accounting for data right across the border that is creating discontinuities between different countries. And in fact, one of the tasks that was given to the project team writing the new version of the code was to prepare a European map of wind hazard based on available data. And the result is this one, which does not solve any problems, just highlights the problem. So the final decision was not to incorporate that in the code. So there was consensus that it's time now to try to produce a European wind hazard map, at least synoptic wind hazard map. And of course, in doing that, as said before, what is becoming very fashionable is the use of reanalysis data. And we don't know whether reanalysis data are good to do that, or at least to supplement measurements. And for example, I'm showing you here some results of some research that we are doing at the University of Campania, just try to compare measurements obtained from a LiDAR with measurements, with data calculated through reanalysis. And here you can see two storms, one in February 2017 and the other one in October 2015. First one, reanalysis data more or less describe what we measured with the LiDAR, but the other one, see that results are totally different. And if we want to apply any of the variants of the method of independent storms, which is perhaps a good way now to process, statistically process extreme value data of wind speeds, what we should be aware that we need to have good and reliable values for storm maxima. Now, this plot shows the largest 100 storm maxima measured over a period of about 15 years at a given site, measured and obtained through reanalysis. So what you can see is there are some values, I don't know if I can use this one to point. No, not that one. Yes. Is there a pointer? No, doesn't work. No problem. Anyway, on the horizontal axis, you have the values from reanalysis. So you can see that there are some values that were calculated through reanalysis that do not correspond to any measurement, and vice versa. Values on the vertical axis, which came from measurements but do not correspond to any evaluated value through reanalysis. And some others, some storms that were detected through the two methods. And we expect them to be aligned, you know, on the bisector of the plot, and they're not. They're just a cloud. So clearly there is a problem with this data, and there still is a lot of work to do here. And the use of large computing facilities, I think, would be very helpful in that. One other aspect is that of orography. What we avail now about the effects of orography on ABL flow and on actions on structure is some material that was published in ESDU, in an ESDU item in the 90s, in 1991. And that again came from numerical calculations that were made in the 80s, again with the limited computational power, considering a shallow two-dimension feature, which is kind of a nice exercise, but it's not reality, it's not what we have in real life. And that was translated again into the Eurocode in the 90s, and then in the current version of the Eurocode, and also in the new one. And that gives some charts where you can find coefficients to calculate the increase in the wind speed that you should be using in your calculation. Increase in wind speed, which is a speed-up effect associated with orography. But of course, as I said, there are much more realistic situations that need to be analyzed. One other item is the flow in the canopy layer and the loads that flow gives to structures. What we are doing now, we are taking the characteristics of the flow at the lowest point in the inertial sublayer, and we are using those characteristics to calculate loads on structures in the canopy layers. That's not true. That's not reality. We very well know that the characteristics of the flow and, of course, of the associated actions in the canopy layer, they're completely different, and I believe that lots of research would be needed here. Just to get towards the end of my presentation, another very important aspect is aerodynamic coefficients, and in the new Eurocode, aerodynamic coefficients have been divided into 3 annexes: Annex B for pressure coefficients, Annex C for net pressure coefficients, and Annex D for force coefficients. Some values, or most of the values, were taken from the old code, some were updated, some new values were added, but the problem remains, as it was pointed out in a paper of Chris Gertz, more than 20 years ago, at the time of the preparation of the current version of the Eurocode to be published then in 2005. And basically, what was pointed out at the moment was that the coefficients available, which are the ones that we are still using, were some of them produced in the 1970s with very limited equipment and very limited, access to experimental facilities. And for some of them, we don't even know the source, so we cannot go back to how they were produced. So basically, we don't have knowledge about flow conditions. We don't have knowledge about the averaging time and the tributary areas that were used to evaluate the coefficients. And of course, more than everything, we don't know what their statistical definition. We have their statistical definition only for a limited number. Just to get to the last item here, I said that we can use, and that's very important to do, I believe, we can use full-scale measurements, full-scale experiments to validate code models, but more than that, I think a calibration of code models, that is the parameters that we use within the code models. And for example, at the moment, we are doing some full-scale monitoring of 80 meters tall building belonging to the University Hospital in Naples. And we equipped that with 16 pressure taps and with accelerometers and with a couple of anemometers and with a static pressure probe. And the idea is to use the data that we can measure in this project to try to check how the models given the Eurocode perform in this direction. Well, my conclusions are very simple. They're just a list of a wish list, let me say, a list of points where experiments can help very much at this stage. And I said first one is try to check whether reanalysis can assist in evaluating wind hazard, and that can be done through climatic reanalysis with the assistance of CFD model as well. Then we need to make more advanced circulation models with considering a common orographic pattern, and that can be done through a combination of experiments using wind tunnel tests, using computational fluid dynamics, and of course full-scale validation will be very, very nice, of course. Flow and associated actions in the canopy layer, those can be measured in the wind tunnel, but also CFD is very helpful at that and very efficient, I believe. And then, of course, there is the aspect of aerodynamic efficiency, and it's a huge chapter. We can try to measure as many as we can and try to improve the data set that we have and perhaps make it become an internet-assisted database rather than figures or charts or tables in the code, which will be very good to do, I believe. And of course, that has to be done mandatorily in the wind tunnel. And of course, validation of the existing models through wind tunnel, through full-scale measurements. Thank you very much.
Thank you very much.
Sorry, just one addition after that. Luca Caracoglia, who was not able to attend the meeting or the workshop today and yesterday, he asked me to show this slide with a brochure of a SISM course that him and Oria Hangan have coordinated. The course will take place at SISM in May next year, and there's a number of people in the audience that will be teaching at that course. Thank you.
Thank you very much. This is a very nice overview of the potential policy impacts, and I'm sure Gerard will appreciate very much this presentation. Unfortunately, we are well out of time, so we'll proceed to the next presentation, and we'll have discussions during the lunch break. Thank you. So I call the third presenter, Olivier Flamand.
Running time.
There you go.
Thank you.
Welcome.
Good. So I will be presenting something more practical. So I'm representing the group of users and the access provider I am for the ERIES VORCI wind tunnel experiment. So VORCI, oh sorry, maybe I have to just remember that the people sharing this with me are mainly from Siemens Gamesa, the company making wind turbines, and some researchers from the University of Genova. So the topic is the freestanding piles, cylinders, that are the masts supporting the wind turbines. Usually when you put them at sea, of course, when they are on the quay side, they are vertically standing close to each other, and they transport them to the site where they post them to the ground, vertically standing also. So the dimension of that is 60 meters high, and the diameter of the tubes we have been studying is 6 meters. So you can see that quite large elements. And the problem with that is vortex shedding, excitation by the wind, creating alternate vortices at the top and shaking these piles in a direction transverse to the wind direction. So this is a representation here of this kind of yeah, the pointer is working. This vessel that is posing this mast, and you have on the left side the size of the model we did in the wind tunnel, so 3.2 meters high and a diameter of 35 centimeters. So the scale compared to the full scale is 1 to 18. And this is a representation, a better representation of the vessel when it is going to the site where it will be posing on the ground this mast. So the amplitude of rolling, that is the movement due to the vessel tilting, is 3 degrees, and we respected that at the wind tunnel experiment. So we designed a special tilting table to sustain the model that was equipped with sensors. And the time scale is not exactly the same, but whatever. Actually, at full scale, it takes 10 seconds for a movement, and in the wind tunnel, it is a 1.4 Hertz, 0.71 seconds. So we have been respecting as much as possible what was acting at full scale, and also, of course, the Reynolds number that is very important. So this model was equipped with sensors, two kinds of sensors, pressure taps for the measurement of the loads. So you have the loads at different levels. Actually, there are not only 6, but 8 levels of measurements of the loads, or of the pressures. And there are also some accelerometers at the top. So some views of how it works when we put pressure taps everywhere inside. And also we have to put the sensors inside to have tubes that are not too long to reduce the effect of the oscillation of air in the tubes. And also because we will be shaking these elements, so we have to attach the sensors firmly inside the model. You can see here the accelerometer on this side here. This is a 3D accelerometer. And you can see this model in the wind tunnel, so set vertically in the wind tunnel. So there are here 2 videos. So I apologize that the first video will be making noise. You can see here this shaking, tilting table in the wind tunnel. So it was quite difficult to achieve the high frequency they needed for the test. But we succeeded in that. Just electric engine, and we changed the power frequency of that to change the speed. And also, I think I can show you when it is operating with the wind. So the same thing, and you can also see the amplitude of this movement that was providing also strong acceleration. So we have to be very careful with the sensors, because of course such acceleration is sensitive for the pressure sensor. I think I can stop all of that. Just to finish with, we have been doing that in 3 phases. The first phase, the wind speed was limited to 40 meters per second in the wind tunnel due to the capacity of the sensors, the pressure sensors. We had 200 pressure taps. And finally, we continue it with 2 other phases with higher wind speed, and we changed the pressure sensors, but we didn't have enough sensors to provide the 200 pressure taps measured at the same time, so we restricted to 64 pressure taps, and it was a challenge also to make the choice of which pressure tap we keep or which one we discard. So some results. So the first kind of data processing that can be done is expressing the mean pressure at the different rings we have here. So the ring 2 is quite close to the summit of the model of the tube, and the ring 6 is 2 diameter below. So you can see the very important difference. So many of you that are wind engineers know about that, but for the others, I will try to explain what is happening here. You have a change with the Reynolds number, that is the wind speed actually. Here, the ring 6, that is representative of what we observe usually in wind tunnels. You can see here the subcritical. We have a base pressure here that is well developed, so conducting to a large value of drag coefficient. And here, when you arrive to a Reynolds number of 3.8 to 10 to the power 5, you have a reduction of the base pressure and a large development of the negative pressure on both sides. So it is first on one side, then on the other side, conducting to a lower, very low drag coefficient that is explaining the drag crisis that is famous. And after, when you go to more and more higher Reynolds number, you have a development of the negative pressure that is much to the oncoming wind. I didn't precise here that the oncoming wind is from the right side, going from right to left. So you have a positive pressure here, of course. And here, at the end, with a quite high Reynolds number, close to 2 to 10 to the power 6, you have something that is very classical of supercritical. And when you look at what happens closer to the summit of the cylinder, it is very different. So when you are completely at the summit, it seems there is no Reynolds number effect. You have something that is very similar, except maybe the size of the base pressure area here, but you don't have a strong evolution of the position of the lateral negative pressure. And if you look to ring 4, that is intermediate between the top and far from the top, you have something intermediate between two. So it's just a mean view of the mean pressures. If you look at this integration of these pressures to have the drag coefficient in the direction of the wind, you can see this famous effect of the reduction of the drag coefficients when you arrive to the critical state, critical regime of flow. And it is more marked on ring 6, that is here, than on the top. So it is as if this famous drag crisis effect was not affecting the top of the cylinder. So now looking at the spectrum, so the spectrum not of the drag coefficient I was looking for before, but of the lift coefficient, that is the lateral force on the cylinder, that is the most interesting force for us in this project, because it is the origin of the vortex shading. You can see here, when you look, ring 6 is what we usually see in wind tunnel. When you are in subcritical Reynolds number, you don't have a very strong mark here, and it disappears also in critical Reynolds number. This is the Strual number here that is supposed to be 0.2. In the code, it is supposed to be 0.2. And it reappears here when you are in supercritical Reynolds number. This 0.2 value of the Strual number is not true for the top of the cylinder. You can see a 0.05 value of the Strual number. So it is very different. It means the vortex shading, if it exists, is not at the same frequency as in the main part of the cylinder. So the excitation by vortex shading will not be the same at the top and in the mean part of the cylinder. So many other things to say, but I will go fast. When we do some analysis, you know certainly the principal component analysis. So if we make that here, it is a special kind, the dynamic principal component analysis. I will explain the differences. That is, we can, from this first mode extracted from the pressure measurement at the 8 rings, we can have both an analysis in frequency domain and an analysis also in the space domain of the appearance of the pressures. So here, what we have been doing here is we separated what happens in this high peak, so the frequencies that are close to 0.05, and you can see that at the different frequencies corresponding to the various peaks here, you have the same schedule of pressure oscillation that is only at the top. When you look at this part of the spectrum, that is 0.2, close to the classical Strual number, we observe here a fluctuation of the pressures. So the pressure pattern oscillating is only considering the lowest part of the cylinder, but not the top at all. So it is the main finding of this experiment. And this dynamic principal component analysis gives also a way to analyze what is acting at the different frequencies. So if we look with the time evolution of what happens in this range that is close to the lowest Strual number, you look, you here have OP, 0P, etc., to half of the cycle of the oscillation. And you can see that it is coming from the left to the right, or etc. So you can see this alternated eddies formed on the top and creating these alternated forces on both sides. So this is, of course, vortex shading, but limited to this part, the top part of the cylinder. Oppositely, if we look at what is happening at the classical normal Strual number, it is only happening at the lowest part of the cylinder, and there is nothing on the top. So it is very important to keep it in mind, because you know that usually people are putting some spirals at the top of the chimney, for instance, to reduce vortex shading. Actually, it is not the classical vortex shading that is acting at the top of the chimney, but another one that is at another frequency, and that is not extended in space. So, about the conclusion, I hope I was fast. So, we have been successful in studying the VIV mechanism. The tests have been performed up to very high Reynolds number, so showing things we ignored before, and especially this tip effect. So the people from Siemens Gamesa, they knew about the tip effect because they were used to consider a different Strudel number for the top. But here we have been characterizing the size of this zone, this area at the top of the cylinder that is not at the same, corresponding to the same classical vortex shading. And so this Strudel number 0.05 is quite different. There is a ratio of 4 with the classical one. And it seems to be valid also in the subcritical Reynolds number, in the supercritical, but the processing is ongoing. So we'll say more on the next conference in Trondheim in June. Thank you very much for your attention.
Thank you. Thank you very much, and thank you for keeping the time, Olivier. We have time for a question from the audience. Yes, Girma? Okay.
Yes, please, Girma.
Thank you very much for the excellent presentation. I was wondering how close was the top of the object, the test specimen from the ceiling? Was there any wall effect? I couldn't tell from the image.
Good question. So the cylinder is 3.2 meters high. It was based on the tilting table that was too high, in my opinion. But it was 70 centimeters. So it means because the wind tunnel is 5 meters high,
Okay.
we still have 1 meter and
Yes.
10 or 20 centimeters.
Okay, thank you. The image doesn't do the justice. Okay. Thank you.
Okay, thank you very much. We'll go to the next presentation now. Thank you. So I ask Ryan Holt to come here for the next presentation.
Okay, hi everyone. First of all, it's a pleasure to be presenting to you all today. So my name is Ryan Holt. I'm part of the ERIES All for Wall project. And I have the task today to present to you some of the results that we obtained through video-based measurements that I guess are, let's say, a cheaper alternative to things such as the motion capture system that I think you might find interesting. So just quickly, this is I guess the table of contents for the presentation. So I'm going to start with an introduction, give you a very brief overview of the experimentation, show you some results, and then I'll conclude. So just to start off, when we talk about structural testing, we usually look at conventional instrumentation, so LVDTs, potentiometers, strain gauges, to really collect that data. A phrase that comes to mind that actually was told to me recently by a lab technician was, to instrument is to disturb. So when you're applying a lot of these instrumentations, you're affecting the structure to some degree. One way, or I guess a different way of capturing that data without really disturbing the structure, there's many different methods, but one is the motion capture system. So we used an OptiTrack system, for example, that uses cameras that reflect infrared light. They detect discrete markers that you essentially apply to the surface of the structure, and they provide very accurate results. The problem with this, of course, is it requires a lot of equipment, and usually it's very costly. So one of the aims for us was really to try and see if we could essentially get the same sort of data, but from a more cost-effective process. So for this, we used digital image correlation techniques. I don't think I really have to explain it too much to the audience here, because I suspect all of you at some stage have either used digital image correlation or have at least been involved in a project with that, particularly with regard to the speckle pattern there. But we also investigated if we could use this technique with targets, so that is glued on or painted targets to the surface of the structure itself. So the idea was to essentially use these targets that you can kind of see down here, the crosses and the circles, to try and derive the same sort of data that you get from motion capture systems. So just quickly, I've put the QR code up on the screen if you're interested in downloading the corresponding journal paper that we recently published. I'll also have this QR code up at the very end of the presentation if you didn't want to do it right now. Just to quickly show you some of the aims of, I guess, this project within the project itself, we really wanted to try and reconstruct the three-dimensional vibration field and extract modal parameters using this system. So using a video-based data acquisition technique. And some of the novelties of this, first of all, was there really is a lack of experimental data, particularly with dynamic tests that use this method. To the knowledge of us as well, we don't really know if there's ever been any study where multiple stereo camera pairs, so multiple pairs of cameras, have been kind of put together to reconstruct a three-dimensional vibration and modal shape identification for these sorts of tests. The corresponding journal paper as well, we present a very simple procedure for the camera placement, the setting up, and the sizing of the targets. So I guess our hope is that this could be used in the future by other research teams as well, if you wanted a more cost-effective way of obtaining a lot of data. So just very quickly, I'll speak about the experiment itself. So this was the ERIES All for Wall project. We tested 2 reinforced concrete core walls on a shake table. The tests were here in Lanec, so I'm glad to be back. I guess some notes, we put 28 tons of additional mass on top of the wall. So this is the photo of the wall pre-test. And the main objectives of these tests were really to investigate the torsional response of the core walls, but also to investigate the residual displacement. So in other words, the post-earthquake repairability. I'm not going to go into too much detail with this project because my colleague João will give a presentation in the afternoon after lunch that gives, I guess, a better overview of the project and also some preliminary results. In terms of the instrumentation that we used, again, we used a lot of conventional instrumentation, so LVDTs, potentiometers, strain gauges, accelerometers, as pictured up there. We also tried to use state-of-the-art sort of instrumentation as well. So this involved distributed fiber optic sensors that were actually glued to the steel rebars within the concrete core. We used a motion capture system, as I mentioned before, so the OptiTrack system, which is pictured here. And we also used digital image correlation. So we had a speckle pattern for the base of the wall, and then we had these virtual targets, the circles and the crosses. And this is essentially the focus of the presentation today. So we had 3 cameras for this, specifically for the digital image correlation of the targets. The first camera, the B1, was essentially set up behind the wall to capture the web. So that's capturing the entire surface of the wall itself. The second camera was essentially set up diagonally to capture both surfaces across the entire height. And the third camera was essentially set up perpendicular to the plane of the flange there. So again, the idea was to have all of these pairs of cameras and essentially try to post-process the data so that they're effectively talking to one another. In total, we had 172 circles and crosses, so the circle and the crosses there, and you can see them at the top of the wall primarily. The reason for the difference in the shapes, so technically we could have had all circle painted on markers, virtual markers, but one of the things that we wanted to try and investigate is to see that not only if we could derive displacements, but rotations as well. And of course, the cruciform target would, in theory, allow us to do this. but we're yet to really investigate if this is actually possible. So that will be something we'll do in the near future. Also, all of the calculations involved in this process are given in that in the journal paper. So, some results. The first video I have, it might be a little bit difficult to see with the brightness of the screen, but essentially you've got red circles that are essentially validating each one of these targets that it can actually see. It might play again where the wall is actually moving back and forth and the red circles are sort of smeared because it's actually capturing the displacement of those virtual targets. It's a little bit easier to see in the next video here. So the circles here are obviously representing each of the markers, the virtual markers that were painted onto the wall. And you can see that the X, the Y is the Z, so the Z is obviously the vertical. If I play the video, this is, I think, under the largest ground motions. So it's really capturing the three-dimensional displacements of each one of these virtual markers. To put this in more relative terms, we can compare the results of these virtual markers, so the displacements obtained, with the more conventional sort of instrumentation, and also the OptiTrack motion capture system. So this is the base of the wall. So the base of the wall was effectively clamped to the shake table itself. And so you can see that there are some virtual markers on the foundation itself. And this is the X, the Y, the Z, and the directions are given in this figure. Hopefully you can make that out in the photo below. So effectively, what you're seeing is the displacement of the table itself. Even though it's the foundation of the wall, it's effectively rigidly connected to the shake table. And in the blue is the LVDT reading, so conventional instrumentation. The orange there is the OptiTrack motion capture system, and the green is the digital image correlation with virtual targets. So what you can see in the X and the Y is effectively just the green lines, and that's because it's such a good match to the motion capture and the conventional instrumentation that it's basically overlaying those lines there. There is a little bit of discrepancy in the Z direction, so we didn't have any ground motions fed in the vertical direction of the shake table. So technically the displacements in the Z are effectively negligible, they're almost zero. And you can see that there's actually a lot of, let's say, noise from this technique. That effectively comes down to the intensity of the pixels that the cameras are picking up the virtual targets. And so the way that we set up this test was to derive large displacements and not small displacements. So I guess with this method, it is technically possible to measure smaller displacements, but we would have needed to change the entire test setup, including the size of the targets on the walls. This is the top of the wall, so the so-called collar or the head of the wall, and you've got the X, the Y, the Z directions there. This is another comparison with some potentiometers. So we didn't have a potentiometer in the vertical direction, but we had conventional instrumentation for the X and the Y. And once again, you're seeing a really, really good match to the conventional instrumentation, effectively validating and verifying this method. There are small discrepancies that you can kind of see here. We think that's actually largely due to the fact that the virtual targets were on this surface here and the potentiometers were effectively around the corner from that picture there. So slight differences in where we're actually comparing this data. So once we have effectively validated this method, we can actually move on to try and derive other quantities, such as doing a modal analysis and getting not only modal frequencies, but modal shapes. And so again, it might be a little bit difficult to see in these figures, but the red circles here are the locations of the virtual targets, and the blue lines here are effectively representing the modal eigenvalue analysis. So you can see the directions of the blue shapes here, effectively indicating the modal shape. The first mode is a torsion flexure coupled mode, whereas I think it's a little bit maybe more obvious. The second mode here is clearly just a rotation, a torsional mode. The calculations and the way that we are actually able to derive this is given in the corresponding paper. I don't have enough time in this presentation to discuss that, unfortunately. So just quickly some conclusions. I think I'm probably within time, hopefully. So this investigation was really trying to look to see if we could derive really important data from a cost-effective point of view. And so we're able to do that, and I think I showed you on the slides before that really it's giving pretty accurate results compared to the conventional and the motion capture system. The other thing is it really significantly enhanced the number of data points that we had from the wall tests. I think we all know that with structural testing, you're obviously limited to the number of physical sensors that you have, but also the number of inputs that you can actually have for each test, depending on the computer system, etc. And so this gives you, I guess, a different method for deriving a lot of data points that can be really important for your tests. So I guess here's the QR code again if you want the corresponding journal paper that we've recently published. Our hope is that this could effectively be used in the future for all sorts of different research projects. Thank you very much, and I'm happy to attempt to answer any questions that you have.
Thank you very much, Ryan, and we do have time for a few questions.
Thank you for your presentation. I'm not sure to understood correctly. For each camera, you have a pair of cameras or only one camera?
Pair of cameras.
Pair of cameras.
Yeah.
This is zero correlation.
Exactly.
Okay.
It's effectively the, if you've ever used digital image correlation for the speckle pattern at the base of the wall, so at the base there, you effectively need two cameras in order to get the three-dimensional field, yeah. So you can use one camera to capture 2D, but two are needed for 3D, yeah.
Thank you. Another question there, David, please. Thank you.
Thanks for the very interesting presentation. I just was wondering if your estimation of the accuracy of the results, let's say in standard condition, then it depends on the distance of the specimen and maybe, I don't know, other conditions, but
yes.
Just to have an order of magnitude.
Yeah, it's a really good question. So there are a lot of dependencies in terms of the accuracy of results. Again, in the journal paper, not the conference paper, in the journal paper we really spell out how best to approach that, because the accuracy of the results depend on a lot of things, such as the size of the targets, the distance away that you're setting up the cameras from the specimen, and a few other things. And so we used a specific program, I think Blender, to effectively determine how best to approach that. And you saw, I think you saw in one of the first videos that I had, again, in the Z direction, the accuracy is a lot worse because it's trying to capture really small displacements. If we had have changed the setup to allow for smaller displacements, we would have achieved, let's say, better correlations, but then we would have had worse results for the larger displacements in the X and the Y.
Sure.
So, yeah.
Okay. Thank you very much.
Thank you.
Okay. Thank you very much, Ryan.
Cool. Thank you.
Now we jump to the presentation by Iksan Bal. There he is.
Start. Okay. Hi everyone, my name is Ihsan. I'm part of the hysteresis project team. It will be a rather relaxed presentation because we haven't done the tests yet. So it's always good when you are not there yet. But we wanted to present the design phase because I will explain in a while, because of the particularities of this project. The design phase itself is, it's always challenging to design an experiment, but here we take the extra mile because it's a geographically distributed experiment and we have to fit multiple criteria all at the same time. So our project is about, as I said, geographically distributed hybrid testing of a multi-story timber structure. And George made sure that we wrote compliant soil here. And today I will talk about how we progress with the pilot design. First of all, the partners are also quite geographically distributed, as you see. We are in the lead in the Netherlands, in Groningen, as Hanse University of Applied Science. And then we have our transnational access at Bristol and Patras at the same time. Then we are cooperating with Norwegian Life Science University in Norway, as well as University of Waterloo and University of Toronto from Canada. What is our motivation? Well, you all know there is a trend in the last years. People don't like concrete because it has a very high carbon footprint, and the construction industry is responsible with the lion's share of the carbon footprint, etc., etc. We all know that. And mass timber has become, also with the help of the industrial developments, it has become more fashion. It started with the tiny houses, but now we are going to large structures. Of course, there are issues, stiffness, serviceability limitations, etc. But it's an increasing tendency to go larger and taller timber structures in order to have some sensible impact in the overall carbon footprint of the construction industry. But there are issues and several question marks in the serviceability design, as I mentioned, but also seismic and wind design. We still have questions on certain issues in reinforced concrete design. So imagine timber design for large structures, it has even more question marks about this kind of design issues and interaction of the elements among each other. Well, if you look at the timber design, it is a bit different than reinforced concrete and steel because basically we keep timber elements elastic and the entire interaction is lumped at the connections. And then the timber design becomes mostly steel or connection design. Of course, if we add on top of this the solid structure interaction, then it is basically the design of different components with lumped nonlinear response. And large-scale testing of this sort is extremely difficult for dimension reasons, but if you add also the solid structure interaction, it becomes, well, nearly impossible to do it in one single facility. So this is our motivation of using ERIES opportunity. Our objectives, first, to understand and improve energy dissipation in timber structures. If you look at the literature, there are numerical studies for large timber structures, and there are experimental studies, but in a relatively small scale, maybe one, there are a few exceptions in the last couple of years, one in the US about this kind of test, but there are very, very few. Then we want to assess also the impact of SSI. Why SSI is important? Well, SSI is always, well, most of times important, but also in the timber structures, these are lighter structures. Basically, if you design the foundation, you don't need as large foundations as you would need in a reinforced concrete structure, but at the same time, it should allow a kind of sensible interaction with the rest of the structure. And in order to achieve all these ambitious goals at the same time, we thought that the geographically distributed hybrid testing as an old methodology could help us. So, ERIES Hysteresis aims to make use of the state-of-the-art testing facilities in Europe and addressing all these issues at the same time. Hybrid testing approach, I think most of you are aware of a hybrid testing approach, but in a very short. If we are talking about a large structure, we don't need to test everything if we know the behavior of most of the elements. So basically we model the structure, we model the things that we know how they behave, and we just isolate, by using certain methodology, we isolate the part that we are not sure. So we test the part that we are not sure how it will behave, and then the part that we know how it will behave, we model it in a computer software, and then we make sure that these two, during the experiment, they interact step by step. So this is hybrid testing. Normally you can do it in one laboratory. You can have a large computer model, and then the part, for example, a BRB, a damper, or whatever, that you want to test, you can put it in the testing rig, and then you can interact between the two. But what is a bit different here is that we will not do it in one laboratory, but we will do it at 2 laboratories at the same time. So the first laboratory is the SOFSI at Bristol, where they have a soil pit. And this soil pit, I will come to that in a while, is suitable for this project because it is a soil pit, but we can also attach actuators to do the test. And then in Strulap in Patras, we can test the other components. But in order to allow this separation, what we call the substructuring, we need to consider all these things already in the design phase, so that when we come to the substructuring, we should be able to properly dismantle the structure into proper pieces and distribute it to different facilities. So our partners from Norway and Canada are helping us with the timber design, making sure that our timber design is also realistic and complying with the Eurocodes. We are following the existing Eurocodes, and at the same time, our design allows us to substructure later. Well, these are the laboratories. On the left, the Strulap, where we will test dampers, which is a component of the overall design. I will show you in a while. And on the right, you see the soil pit of Bristol. What is the state of the art? Well, as I mentioned very briefly at the beginning, there are some tests at the component level, like BRBs connected to timber elements, different types of hold downs, although it's exponentially increasing this part of research, different types of hold downs in the sense that low ductility, high ductility, recentering, not recentering. Recentering is an important issue in timber structures because, again, they are light. And there is not enough restoring force most of the times to put everything back at the end of the earthquake or lateral load. So the recentering systems are even more essential for timber structures. Despite this growing knowledge, and exponentially growing knowledge, I have to say, the timber system interaction using different elements, for example, different type of hold down and then another type of damper and the soil structure interaction altogether, this is still limited. And the advanced hold down systems, yeah, they are increasing every day. There are different systems tested. But what is important, if you just zoom out and look at the whole thing from a structural engineering design perspective, let's say that you are working in a design office. A behavior of a single BRB or behavior of a single hold down is of course important, but what is important is the hierarchy among all these. Because we all come from earthquake engineering background, well, most of us come from earthquake engineering background, so this hierarchy is something that is an essential part of the design. If one of the elements is reaching yield way later than the others, well, there's not much point of the energy dissipation in that element because it will never reach that level because the other elements will fail before. So this hierarchy is something that we are looking for in this test. If you look at the approach of hysteresis, well, we start with a 3D pilot building. That's on the left. We have already done that part. We want to get the overall geometric dimensions and acting forces. Acting forces are important because this is a limiting parameter in the experimental phase later. Then we extract a 2D frame from this 3D structure, and then we start breaking down this frame into pieces, which is what we call the substructuring. In the 2D frame, we have to get the test specimen dimensions, details, acting forces, displacements, to find the stroke capacities and the loading protocol. And in the substructuring, we should be able to make sure that a 2D frame analysis and the substructured 2D frame analysis, they match. They are exactly the same thing. At the moment, we have completed the 3D pilot building design. We extracted the 2D frame from the 3D, and we are at the phase of substructuring. But the design step was a bit tricky because it's a very long phase. You have to start with building the structure and adding pieces together, etc. But at the end, you have to make sure that the forces at the actuators and then compatibility, because we are not modeling the entire structure in the laboratory, we are just modeling one part of it. Compatibility, at 2 laboratories are all satisfied. So this needed a lot of iterations. After doing it a couple of times manually, we decided to do it more systematically. Basically, it's simple. We start with a fixed design data. We chose Athens because it has a relatively moderate seismicity and relatively moderate wind loading conditions. So we take this as given. We take the overall building dimensions and the number of floors as given. We don't change those. And then we start with the design input parameters, dimensions, weight, slabs, etc. Then we go to the non-linear element properties. We choose hold downs, the capacity of the hold downs, the capacity of the dampers. We do our analysis, and then we check the required actuator forces, physical dimensions of the specimen, stroke limitations, etc. If it is not okay, we do the circle again. And after doing it several times, we decided to create a Jupyter notebook for this. It's a parametric design. We shared several versions of this with partners during the design. If you change the story height, you don't have to do everything again. It has an embedded OpenSys model inside, so it will do all the analysis. It will find the mode shapes. It will go to the spectrum, find the earthquake force, and then redesign everything accordingly. This is our 3D pilot design. It's a relatively simple structure. Here we have, well, if you were an architect, probably you wouldn't like this, but we don't have an architect in the team, so everything goes pretty smooth. We have here the CLT walls, also symmetric in both axes, and in the corners we have bays with dampers, which I will show you in a while. It's a simple structural configuration. What is important is that all the columns are hinge at the ends, truss elements, so they are only carrying axial load. We don't want them to interact in the lateral load carrying because otherwise it becomes very complicated. And it's a common design, I can say, for example, in prefabricated concrete car parks and large structures. This is a common design practice. In order not to have non-linearities at the column bases, you just lump them into lateral load-bearing bays, where you can have a damper or chevron braces, etc. So this allows us to basically focus all the non-linearity on the dampers, these red bays, and on the CLT walls. This also allows us to extract just one frame from the entire structure. So this one frame is like the other frames, and it is one of the 4 frames that carries the lateral loads. If we focus a bit on, our floors are CLT. We also made sure that it is realistic. We comply with the serviceability limits, sound insulation, etc., etc. We found the loads from that. And then we extract a frame from this. In this frame, we have the dampers on the sides, and then we have the CLT wall in the middle. The CLT wall has 2 hold downs on the sides, and then in every floor on this base, we have the dampers. Now, focusing a bit more on the behavior. It's a 5-story structure, as I mentioned, so the CLT wall basically remains elastic during we have also done non-linear analysis. You can see the results also in the paper. But the CLT wall remains elastic. That's the design principle. And the entire non-linearity is at the base. So basically, it's a rocking structure. And as it rocks, one side is on tension. When it's on tension, the hold down doesn't work. And it's just lifting on the other side, and then the hold down works in tension on the other side. So it does this motion symmetrically. And then at the floor levels, we have the dampers. Now, the dampers our dampers will be dampers that are already tested by University of Patras, and it has already been published. Why? Because we have very good data about the behavior of these dampers. One of the important things in the hybrid testing, I'm not expert in hybrid testing, I'm just repeating what Osanka told us. What is important is the initial stiffness. So we really have to make sure about all the initial stiffnesses are correctly in place for the stability of the algorithm. So for these dampers, the team from University of Patras, they have given us all the data set from all the past tests So we can see the initial stiffnesses, also all the hysteretic loop of all types of tests. Why I say all types of tests, it's only one damper, yeah, but depending on the pressurizing level of the sand, the behavior changes. And okay, one good reason, because it's convenient, this has already been tested, Patras knows exactly what to do with this damper, they know exactly how they behave, but at the same time, it's rate independent. So if we go with an earthquake record, just don't forget that the test is going very slowly, so there is no velocity. If this was a rate-dependent damper, we would have issues. This wouldn't be possible. So basically, it's a rate-independent damper that allows us to go quasi-static.
Iksan, can you please wrap?
Yeah, I'm just fitting in the lab and then I'm finishing. Thanks. Yeah, these are some drawings from the team in Bristol. We looked, I'm sure until the test this will change several times. But the soil pit in Bristol is 4 by 6 meters in plan and 4 meters in depth, which is pretty good. George needs at least 2 meters and maybe more for the soil, so that gives us a physical constraint. And then when we put all these things together, we are coming to something like this. All the dimensions here, soil, etc., are figurative. We don't, these are not exact dimensions, but the system is more or less something like this. Why? Because it allows us the CLT wall to rock at the base without having a shear, so maybe a solution, something like this. And then on top, we should be able to control the degrees of freedom. This is, I think, my last slide. What I mean with the degrees of freedom, at the top of the ground floor, we cut the structure. We have only one floor high CLT, and on top, we should be able to control the moment and the axial and shear. And this can be done by 3 actuators, all synchronized at the same time. Conclusions. We will use a hybrid testing approach, but distributed to different laboratories. That is essential. We start the 3D pilot that serves to a realistic design, but it also serves to the purposes of this quite complex test. We have created a parametric design framework. This is how we managed to come up with the design that satisfies all these conditions. We start the substructuring phase. And then after that, we will probably go to the next phase of the initial tests. That's all. Thank you.
Thank you very much, Iksan. We don't have time for questions now. We'll have them during the lunch break, which we are all already using. So I thank you again, and good luck for this very challenging test. And I call for the last presenter, Luigi Di Sarno.
Good afternoon, everybody. Thanks for staying here and sacrificing part of your lunch. My presentation is not going to be too long, but what I really want to show is the benefits of having used successfully the structural lab as second part of a project that started also during the previous series, the SERA program. So this morning I'm going to present the column-based plate connection, which is something that typically we have ignored in the past, particularly when it comes to the assessment in Eurocode for steel structures. Typically, we are more concerned with reinforced concrete structures, and when we look at existing structure, we have been assessing it, starting, as I said, with the last project, SERA. We were successful in assessing the response of the frame that performed well under a sequence of earthquakes that occurred in Amatrice 2016, but also we were successful in testing a number of aspects that typically are ignored in code of practice, and that was part of this project called ERIES. So in the wake of this project that was also successfully in terms of publishing and impacting the code, that I believe is very important, we have then been motivated to continue and to move from heat frame to heat base. So a very simple topic here, but often very ignored, not well investigated in a number of codes, in Eurocode, but also in the American code. And thankfully, we had a discussion with our colleague across the ocean that also gave us, at the beginning, some hints. So the project here is primarily focusing on the poor performance of column-based connection. So no composite action, simple still, bare still. But what is very important to note is that we don't know how this system behaves. There are a number of cases that relate to industrial building, but when it comes to residential building, we do not have enough evidence, engineering evidence, to show if these systems behave well. Of course, they are not code compliant, at least to latest Eurocode version. So we investigate the response. In fact, the ERIES 8-based project is aimed to experimentally test base column connection under biaxial moment. So we also want to consider this interaction. But more importantly, we also would like to focus on something that often is ignored and is very important for existing structure, i.e. how structure will behave when we consider a sequence of earthquake. There is a multiple demand imposed, and because these are structures that will show degradation, do they behave properly? So the objective, to point them out, is to investigate, as I just mentioned, biaxial bending, but also, importantly, there is no really fixed set of limit states for this structure. It can be a sort of extension or new structure, but also there are some peculiarities that require further assessment, and also associated safety criteria. In operational terms, we need also to consider how possibly we are going to modify existing code approach. In the case of steel structures, the component approach that has been used quite extensively for new structures, but when it comes to existing steel structure, we don't know if it is working. But more importantly, when it comes to base column connection, there is not enough evidence being built through the past experiment. Of course, we have used this, the test that we have been performing, also to build then the computational part, fragility curves, that also allow us then to move to the earthquake losses estimation. This is also always very important when we want to determine how these models and how existing structure will behave and what will be the impact after earthquakes. To narrow down, in terms of experiment, we were lucky enough to be awarded during the first phase. So at the time to focus on an existing building and to be realistic as possible. We made reference to the building you see here shown on the slides, two-story, seismically designed steel frame. Of course, we did not have the capacity to test the entire frame, so I had to make some assumptions, and the assumption was to make it as realistic as possible and to include as many variables, design variables, in the test. And in fact, we considered two types of column, but also two types of connections that allowed us also then to calibrate, we are at that stage at the moment, our model for further analysis. So that's the frame as mounted in Structural Lab. As I said, that was our access facility. Thanks for also the hard work Statis and his colleagues. We were able to run the test on time. You see that this is also a type of problem at the interface between steel and concrete. In fact, there is interaction between the steel details, but also how it is connected to the block, which is sort of reinforced concrete-based design. More importantly, we were also looking at the type of anchors that are smooth bars. So there are also some issues related to the fixed end rotation. And as I said, we want to be as general as possible. So it was a single-story building, 3 meters times 5 meters, but roughly, and 1 meter block. But what was interesting about it, two types of connection, pins on one side and fully rigid on the other side. And I'll give some of the details here. How did we design this? There are not so many examples in an application, as I said before, particularly when it comes to residential buildings. So we went back to what was the practice during the 60s, for example, when these connections were firstly used, particularly in south of Europe. And this is what we ended up with, some old drawings that we obtained, particularly in Italy. There are some booklets Italsider issued, where they provided some details like this for stiff joint, and also for the case of the unstiffened base connection, we had something like this, which we reproduce on site and well, only for 2 cases. It was mentioned before that sometimes we instrument to disturb. We tried not to disturb the basis of the column, but it was densely monitored, because here what we want to do is really calibration at local level, but also at global level response analysis. So we have a very dense setting of LVDTs, but also DIC. That was also another element that we use, inclinometers, as you see, both at base, but also along the height of the column, to read particularly the unbalance, hence the torsional motion that I'll show in a minute. In terms of experiment, on left side you see the input we used. We were consistent with the type of input motion that was used initially in 8 frames, which was basically the sequence of 2016 Central Italy earthquakes. There were 2 records, and in this case, that was the challenge, the extension from the previous project. We also applied it bidirectionally, which is something very interesting, particularly when you have this type of connection. So on the right side, you see the type of, that's an aerial view of the test setup with the 2 controllers applying externally with 2 rigid elements here, the forces, and also on the other side, that's the orthogonal controller number 3, showing the out-of-plane response that also was applied. In terms of test matrix, this is a summary, very briefly. Of course, you are aware that when you perform pseudodynamic tests, it takes some time for running them, so we had to frame within the allocated time. So firstly, free vibration tests, X and Y direction, because we want to be sure also to catch the frequency, and later on to calibrate based on numerical model. Quasi-static text at larger displacement without creating too much yielding of the system. But then we pushed the system through an experimental IDA up to 1.2, and then considering only Y direction, we brought to the failure with the large drift of the system. So 1.5 was really the ultimate condition that we have explored. So having highlighted the test matrix, I hope it, yes, is working. So you see that the system is moving and the eccentricity is taking place. So left side, you see the overall response, but also on the right side, you see that for the stiff and strong elements on top of it, base column connection, with all the stiffness in both directions, it's not really happening anything. So the system is behaving as a rigid body. But when it comes on the weak elements down, which is the unstiffened element, basically is rocking, which is something that we should account for, because it can save a number of frames. In this case, a very simple one, but also at, when it comes to higher story, because of course there is a cut of the maximum force with some slippage taking place. And of course that's part of the discussion that now we are considering, because of course here you can have some damage concentration, and that's exactly what I'm going to show in a minute. So what we have observed, observation here is fundamental, because there are not so many data, as I mentioned before. So just a summary of the observation we did on site. Large torsion, as shown before also through the animation, but more importantly, there were a number of localized damage that one could not expect if relying on existing details as implemented in Codo practice. And those of them are summarized as a fracture at welds. These are critical, because if you start to lose cracks, so the system starts to lose its continuity, and of course it can go any direction, particularly if you have similar action in both directions. So we observed, as shown on top of the slides there, in the circle, the fracture of the welds at the top beam-to-column connection, but also some of the plates start to bend because there was not enough stiffness, and there were, again, local concentration of damage, as shown there with the distorted plate. We also looked at interface. As I said, another critical component. We should always look at what happens, particularly when you push the system beyond certain limits of interstory drift. In this case, there was a large crack formation at the base, which can be hidden, particularly if the system starts to rock, and you can't see from outside. But of course, it will require some additional retrofitting, particularly because it is hidden in the foundation block, and sometimes it's also difficult to access. Now, the data are there, and luckily we were also able, thanks also to the the schedule, very fat schedule that we followed at Patras to publish the data. As was shown this morning, I was very happy to see that there have been a number of access also to the heat frame and both heat base, based on what Statis was mentioning, but also we started to analyze the test data. The identification of the system, as shown on top with the FFT spectrum, shows that the periods are pretty different, of course, as expected, to different directions with different stiffness, 0.6 and around 0.4 on the other direction. And also, there are some rotation, relevant rotation, that we have measured on site. Now, are we able to simulate this? Of course, we are doing and adopting a sort of progressive, complicated, more refined approach here with a simple model, versatile, but computationally efficient through OpenSys. You see here that we can get some of the results in one direction, but when it comes in the opposite direction, Y, there is a very large variation, which also reminds us that connections plays an important role, particularly in bare steel structure, particularly in bare existing steel structures. So we move to the next step, and the next step is the one that we are currently working on, how we can then refine our model, how we can then come closer, possibly, to what is the response observed. And hence, we are relying on an abacus model, where we are accounting for the details of the beam-to-column, but also base-column connection. As you see here, the slab has been modeled with the concrete element. So coming out of all of this, these are some of the preliminary. I'm getting close to the end, so I hope I'll be on time. Some of the results he's doing on his own. Okay, I think, okay, going back. So basically, as you see here, the cyclic test, well, that's the input, but also by using now a model that accounts for the flexibility of the base column connection and the beam to column connection, we are able to match closely, we are not satisfied enough, the global stiffness. What about the local stiffness? There's been a couple of papers published. There are some good and close match results, but when it comes to the overall system, sometimes you get mismatch because you can model it locally, but then there are additional components, particularly in this case, where torsional balance is important, then requires further assessment for the calibration. So this brings me to the conclusion, which says that basically we are currently focusing on the improvement of the abacus model. We hope to also consider, that was part of the project, probably hidden in what I've just shown now, that we also want to use AI for developing a tool for the component methods. Component method is something very tedious and very cumbersome in terms of use. So why we don't use genetic algorithm to model, to calibrate model that then can be used automatically to determine stiffness, strength, and ductility of the system. That's our aim, and of course, performing fragility, which is another important tool that we typically use, and finally, earthquake losses evaluation. Thank you very much.
Thank you very much, and for keeping the time. We have time for one question, and then we go for lunch. Yes, Roberto, in there.
Thank you.
Okay.
At the beginning of your presentation, you were referring to the component method.
Yes.
That ERIES 3 part 1. As you know, we can say it's a bit tricky. You need probably software or numerical. What's your idea on moving somehow to the United Standard approach that is the pre-qualified
Yes,
joint?
actually that's
what you are saying there is quite close to that.
Yes, yes.
Life easier for
Yes, yes. That's a very good question. Actually, I didn't mention because, of course, of time was concerned, but we are also lucky here to have one of the liaison person with Eurocode that has been doing a lot of work within RSCS on pre-qualified connection, new. The problem here is that we are dealing with existing component, with existing joint. You are right, but this is something that can be easily delivered for a number of new beam-to-column and both either beam-to-column and base-column connection. When it comes to existing one, provided that you have enough engineering evidence, then you can go back and qualify them. But I would say that the number of variables that are in place, because there is no standardized practice, does not allow you to simply go back to pre-qualified. No concern at all, fully agreed for new. When it comes to existing, I would say, need to think more.
Thank you very much. This closes this morning session. For the lunch will take place in the same room as yesterday. And for those who wish to visit and didn't visit yesterday, or wish to visit the other facility today, we will have visits for the shaking table and the wind tunnel facilities. For those who want to do that, I ask you to have a quick lunch and to meet at the coffee break area around 2, please. Thank you.
Just to mention, Antonio, we will have a quick photograph outside before lunch, okay? So don't run away.